so the stuff all about sets is not actually linear algebra. That's just a language we're going to use to be able to talk about linear algebra. So today, this lesson is going to be getting into the beginnings of linear algebra here. We're going to learn how to use the method of elimination to solve a system of linear equations. You probably already know how to do that. And then we're going to learn a new method for solving a system of linear equations that uses matrices. So we're going to solve this using elimination. I'm going to do it like add a little bit of like seems like extra work because we're trying to sort of mechanize the way we do elimination so you can do an algorithm that will just always work even if it's like an extra step or two. All right, so my rules are you can, when you're solving a system of linear equations by elimination, you can replace one equation by the sum of itself and a multiple of another, or you can interchange two equations. You could change the order you write them, or you could multiply all the terms in an equation by a non-zero constant. So if I want to solve this equation using the method of elimination, what would I do first? Multiply the top one by positive 2, because then I'm going to add them together. Okay, so if I multiply the top equation by 2, I get 2x plus 10y equals 14. And then typically what I do is you add that to the other equation. Those terms go away. Can everybody see that color blue okay? Is that right? Okay. So I get 3y equals 9. That's a new equation, a brand new equation that popped out from what I just did. Okay? That's a replacement. I'm going to replace one equation by the sum of itself and a multiple of another. So I'm going to replace the second equation because I added the second equation to a multiple of the first equation. Okay, so my two new equations are going to be the first, the original first, x plus 5y equals 7, and then this new one, 3y equals 9. So I replaced one of my two equations with the sum of itself and a multiple of another. All right. Now I can use this multiply all the terms in an equation by a non-zero constant. That second equation, what do I want to multiply everything by to solve it? What's the solution to 3y equals 9? 3. How do you get there? Multiply by 1/3. Yeah. Yeah. Yep. You can think of it as just dividing by 3. When we do the algorithm, we tend to just use multiplication. So now I'm going to have two new equations again. Two new equations. The first one doesn't change. I'm going to have x plus 5y equals 7. And this one is going to be y equals 3. I can replace an equation with a multiple of itself. And then last, I can back substitute, right? I'm halfway done solving. I know y equals 3. Back substitute in the other equation. X plus 5 times 3 is 7, and you get x equals -8. So everybody's seen this before, right? You know how to solve two equations, two unknowns. All right. So in that equation, all the important information is contained in the coefficients and the constant term. The name of the variables is completely unimportant. X and Y could as easily have been A and B, right? So I can encode all of that information into a matrix where I'm going to put the coefficients on X in the first column, the coefficients on Y in the second column, and the constants in the third column. So x plus 5y equals 7. My coefficient on x is a 1, on y is a 5, and my constant's a 7. And then I have -2, -7, -5. Now, your textbook does not put a line right here to sort of indicate the equal sign, that's where the equal sign belongs. But if you go on like Khan Academy or something and watch videos on this, a lot of videos will put a line there. So just so you know that that's an alternate notation. And you can use it if you like it, it's fine. All right, so this matrix I just created, 1, 5, 7, -2, -7, -5, it has, we say it has dimensions 2 by 3 because it has 2 rows and 3 columns, and you always give dimensions of a matrix rows, columns, 2 by 3. So the same basic maneuvers you can do on equations, you can do on rows of a matrix. You can do replacement, replace one row by the sum of itself and the multiple of another, interchange 2 rows, and you can scale a row by multiplying by a non-zero constant. So I'm going to solve this system using the matrix and row operations. All right, so I start with 1, -2, 5, -7, 7, -5, and I kind of like having the line there. Okay. So my first step is that I'm going to do a replacement. That's what I did when I was solving the equation. I replaced an equation with another equation. So in my first step, I'm going to do a replacement. And I'm going to replace row 2. Okay, row 2 is going to be replaced with itself plus a multiple of another row. Okay, so replacement means you can replace a row with the sum of itself and a multiple of another. So what is the multiple of the other row that I should use? 2 row 1. Yeah. 2 row 1. Okay. Now keep in mind that row 2 is the only one getting replaced. Right? Row 2 is going to get replaced with some stuff, but row 1 is not changing at all. So you just copy that down before you even do any work. Okay. If you need to, it can be handy to write out the arithmetic of the replacement as a little side work. You don't have to. If you can do it in your head, it's fine. But row 2 is going to be replaced by row 2 plus 2 row 1. Okay, so row 2 is -2, -7, -5. 2 times row 1 is 2, 10, 14. Add them together and you get 0, 3, 9. This is your new row 2. 0, 3, 9. That's your old row 2 plus twice row 1. All right, so this is just side work. You can show it or not show it. It's up to you. All right, next. I'm going to scale one of my rows. If we scale row 2, row 2 is going to get replaced by 1/3 of row 2. Notice that row 1 doesn't change at all. It's going to be 1, 5, 7. And row 2, if I multiply each of these entries by 1/3, I get 0, 1, 3. And then you can quickly translate it back to equations and back substitute to solve. So this says 1x plus 5y equals 7. And this says 0x's plus 1y equals 3. So back substitute, x plus 5 times 3 equals 7, x equals -8. So this was a very simple system to solve, and it kind of seems like, why would you do all this stuff with matrices when you can do it real fast using methods that you probably knew years ago? I chose a really simple example to explain the method, but the examples are going to get much, much bigger and much, much harder, and you're going to love that you have this and not have to do it by substitution and elimination. So that's the basic idea of the method. Instead of writing out whole equations, write out just the coefficients, And then you can use the 3 rules: replacement, scaling, and swapping rows. All right, so like I said, these problems are going to get much, much bigger. So when you have a single unknown, we usually use X. 2 unknowns, X and Y, 3 X, Y, Z, but now we're out of letters, right? If you had 4 unknowns, I guess you could use A, B, C, D, but that can only go up to 26 unknowns. And there are problems that will have more than 26 unknowns. Not that you're going to solve them by hand, but so instead of naming with different letters, we name them X sub I. And so for 3 unknowns, instead of X, Y, Z, we would use X1, X2, X3. So here's our general algorithm for solving a system of linear equations using matrices. You want to use equation 1 to eliminate X1 from all equations below it. That is, you're going to use row 1 to eliminate all the entries in the first column below row 1. So if you go back and look at what we did, my first column had a 1 and a -2. I wanted to make that -2 into a 0. Oops. So in my next step, I turned that second entry into a 0. I wanted everything below that first one to be a 0. And then ultimately, you want your next entry to be a 1. Okay. Your next entry in. So you use row 2 to eliminate all entries below in the second column below row 2, etc., etc. Do this until your matrix is in triangular form. A triangle of zeros will appear in the lower left. So when you only have 2 unknowns, this is triangular form because you have a triangle of zeros in the lower left. In this case, it's only 1 0. So this is hard to you need to do an example to see what they're talking about here. So in your group activities, it's going to walk you through every little step. It'll tell you what moves to make in this first example, and then hopefully you'll start to be able to predict what the moves are. All right, so there's just a few minutes left in class. Everybody made it through number 1 and was doing well there. So I'm just going to point out what our homework is for Thursday. So there are 3 worksheets that were you started some of them in class. There's the Sedek and Gallo worksheet, there's the writing proofs worksheet, and the background worksheet. Then there's also some homework from 1.1, which is on solving systems of equations using matrices. So again, that is all due Thursday, but you can hand it in, show me up to a week late with no penalty. So that is kind of a lot for the first night. And then your reading for Thursday is sections 1.1, 1.2, and 1.3. 1.1 we covered in class, so that reading it shouldn't be too difficult. And then also don't forget to bring in 1 easy answer question on Thursday that can come from any of those 3 sections. Questions about what you have to do for Thursday? Yeah. The videos right after class. I upload them right after class. And the notes too. Yeah. I meant to point out the Moodle site. I had it open, but I didn't say anything about it. So on the Moodle site, we've got my notes on the reading. They don't start till 1.5 because I started them last semester at 1.5. I don't have 1.1 to 1.4 yet. But so if it helps you, you can you can look at those to maybe help you make sense of the reading. It's just another resource. The 3 packets, video playlists. So I'll put up the video from this particular class right after class. But then if you, for some reason, you want to work ahead or something, you can look at videos from the previous semesters if you want. And then there are solutions manuals to the textbook posted, so you can use electronic. I believe there's also a binder of solutions in the studio and the library, but I will double check.